Hi, today I will continue with this BDHI indicator. And this is the electromechanical assembly. We can see we have synchros and motors. Therefore, it seems that we have a classic system using a control transformer, a servo control amplifier, and an AC motor. So we can see that we have effectively 3 AC motors, as we have seen in the previous episode. And we can see that we have several control transformers. For example, we have one here, okay, control transformer. So therefore, there are 3 servo controls on that thing because we have 3 things to move. The first, the compass card. So we have the dual pointer here. So this dual pointer is used generally for the EDF, and there is a single pointer here, which is used normally for the VOR. Okay, and the rotor of this control transformer gives actually an error voltage. This error voltage is amplified and is fed to the motor. Okay, I don't know which one is associated to this one. Okay, it is this one here. Okay, so when the error voltage is null on the rotor, so therefore the angle of the control transformer is identical to the angle of the shaft of the synchro transmitter, with a difference of 90 degrees. You can always adjust the position of the control transformer. If you change a little bit the angle of the control transformer, it will have a direct effect on the position of the needle, which is concerned by the control transformer. It is not the case for the motor. You can change the orientation of the motor. For example, this one, it will have no effect because it is inside the loop. So therefore, there is always a servo amplifier between a control transformer and the AC motor here. The servo amplifier can have different shapes. It can be a module like this one. It can be a PCB, but it can be also a small module like that. You can place this kind of servo amplifier on the same mechanical assembly, so therefore you have a complete thing. But I did the complete reverse engineering of the electronics, which is here, and I didn't find any servo amplifier. So therefore the servo amplifiers are located on this assembly here. Okay, so we have 3 servo amplifiers on that unit. Can you see them? It is the first time I see something like that. Actually, the servo amplifier is located on the back of the motor. This is this blue assembly here, okay, which is on the back of the motor. You can see, so there is a small round PCB here. So I assume that we have a servo amplifier which is located on that small PCB. Okay, so we can see we have one servo amplifier located on the back of each motor. There is another one in the center here. There are 2 advantages. First, it permits to reduce the size of the unit, so you don't need to have another PCB or other modules. And the second advantage is the wiring, because you have, of course, the output of the servo amplifier, which is connected directly to the motor inside, and the input of the servo amplifier is connected directly to the control transformer. There are different methods to set the pointers, at least the dual bar pointer, the yellow one here, the compass card and the single pointer here can be set using external synchro transmitters. The dual bar pointer here can be set using an external synchro transmitter, but it can be set also using a digital input, which is probably an ARINC 429. Okay, so for the moment I have connected these 3 things to 3 synchro transmitters we can see here. Okay, so there is also the flag here. So in order to activate the flag, we need 3 conditions. The first condition is the presence of an AC voltage for the reference winding of the AC motor. The second one is a small error voltage on the control transformer. The third condition is the presence of a 28 volts DC voltage on a particular pin, which indicates that the horizontal gyro works normally. So I have simulated this voltage using this switch here. Okay, let's start by this one, because this one is for the single pointer. So you can see that it is a little bit unstable. Okay, so the second one is for the compass card. So you can see that the flag is activated during the movement, because in that case there is an error voltage on the rotor of the control transformer. Okay, and the last one is for the dual pointer, the EDF actually. This is the block schematic of the digital drive of the yellow pointer here. The input is here. There are two lines A, B. So this is the classic ARINC 429 interface. These two signals are fed to a specific part called ARINC 582. At the output, there are two lines, clock and data. These two digital signals are fed to another specific part, which is called register. 12 bits are extracted, and these 12 bits are fed to a digital to resolver converter. At the output, there are two AC signals. The amplitude of the first signal depends on the sign of the angle, which is defined by this digital data here. The second one depends on the cosine of the same angle. These two signals are fed to two different things. First, there is a resolver to synchro converter here. At the output, there are two signals relative to ground. The input of the servo control is of course a synchro. These two inputs can be connected to an external synchro. It is what I have done for the first test. Otherwise, this synchro input can be connected to the resolver to synchro, so this permits to set the pointer according to the input data. Otherwise, the synchro input can be connected to a second synchro here. The shaft is linked to the compass card. This device is actually a resolver to synchro converter with an offset which is the compass card angle. So that means that the position of the pointer is relative to the compass card. So if there is a change of the position of the compass card, there will be also a change of this pointer here. I called this mode relative mode and absolute for the first mode here. The terminology is maybe not correct. I am not a pilot. There is another source, which is this transformer. This is a kind of home position in case of error. Okay, so for the test, I have modified the firmware of my ARINC 429 generator here in order to set the angle by step of 15 degrees. Okay, so it is possible also to change the mode using these two keys here. So for the first test, this is the absolute mode. Okay, it is possible to change the position of the dual pointer by step of 15 degrees. Okay. There is also a clear function here to set to 0. Now we can see that there is no change if I change the compass card here. The second mode is something which is relative to the compass card. So I will change the mode. I think it's 6K, okay. And you can see that now the position of the dual pointer is relative to the north of the compass card here. Okay, you can see that the dual pointer follows the compass card. That's all for this BDHI indicator. It took me approximately 4 days for the first episode, the DME indication, and approximately 1 complete week for this second episode. Thank you for watching and see you next time for another video. Bye bye. You can see here on the right the servo control of the dual pointer here. The AC motor is here. The servo amplifier is inside the motor. The input of this amplifier is connected to the control transformer, this one here. There is a gear train between the motor and the control transformer. Okay, the pointer is of course linked to this shaft here. In order to set the needle to a given position, we need to apply here a synchro voltage. Actually, there are 2 voltages regarding the third one here, which is connected to ground. So it is the same for the compass card and the single pointer. The only difference is that for the compass card, the single pointer, the control transformer here is connected to the rear connector. In that case, a synchro transmitter must be connected to the control transformer in order to set the pointer. In that case, it is different. We can see that there are several switches. First, we have an external mode. In that case, this mode is identical to the mode used for the compass card and the single pointer. We can see that this signal I called extern permits to select between the external mode and an internal mode, which is actually a digital mode. So let's see how this thing works. So here we have 2 synchro signals, okay, in digital mode. So we can see that we have a first selection between these lines here, okay, and these 2 signals which come from a small transformer here. Okay, the selection is done using a signal I called digital active. So that means that in digital mode, if nothing is received, this line will be at low level. So in that case, the synchro is connected to these 2 voltages out of phase. And if you connect 2 voltages out of phase to a synchro, this will give 0. So this is a kind of default position or home position. We can see that in the digital mode, we have the choice between 2 sources, this one and this one. Okay, so we should have synchro signals on these 2 lines and also other synchro signals on these 2 lines. So let's start by this one. So on that path, we can see that we have this circuit. Okay, so this circuit has 2 inputs here, and these 2 inputs are connected to a particular part, which is this part here. You can see that the original reference was erased mechanically. It is impossible to see anything. And this part has also an AC reference voltage. So it was not complicated to find that this part is actually a digital to resolver converter. So these 2 lines correspond actually to resolver signals, and this circuit is simply a resolver to synchro converter. So now let's see the second circuit, which is a little bit more complex. So we can see that the synchro input of the servo control is connected to this synchro, which is linked to the compass card. And the rotor of that synchro, which is actually a resolver input here, this permits to convert resolver to synchro, but also with an offset corresponding to the compass card. And the resolver input here is connected, of course, to the same signals which come from the digital to resolver converter. So what is the difference? The difference is the shaft here. So this circuit permits to set the pointer with an absolute position relative to the indicator itself, and this one permits to set the pointer relative to the compass card. In other words, if there is a change of the compass card heading, there will be a change also of the position of the dual pointer. Therefore, the dual pointer follows in that mode the compass card. So this permits to set the pointer relative to the compass card. We can see on that page something interesting. So this circuit is not used for the normal use of the unit. So these two lines come from the digital to resolver converter. So we have the resolver signals here, they are amplified, and these two outputs are fed to a synchro resolver with a locked shaft here. Okay, so we can see this corresponds to this guy here. You can see that the shaft is locked. So actually this synchro resolver is used as a transformer. Okay, so we have actually a repeater. We have a resolver on the rotor and a resolver on the stator. So this is equivalent to two independent transformers. Now this is the schematic of the front end, which is something interesting. The input is here on the left. So this part is called ARINC 582. Okay, so which is this part here, but this part is used probably as an ARINC 429 interface. Okay, so we have two inputs and two outputs. So I guess that we have a data line and a clock line. We can see that we have also an RC network connected to this part. This RC network is connected probably to an oscillator circuit inside in order to have some timings used for timeouts and other things. These two lines are fed to this part, which is the register parity gate part here. Okay, so this permits to decode the informations, and we have 12 lines here connected to this part, as we have seen this thing. So this is this part here, and this part is a digital to resolver converter. It can be maybe interesting to see after the test what is inside. So this is a hybrid circuit, probably using a ceramic substrate. So here we have an AC reference voltage, okay, on that line here, and we have two outputs. So we have two AC signals. One amplitude depends on the cosine of the angle, okay, which is set by these 12 bits data here, and the second one of the cosine of the angle. Okay, so these two signals are in phase or out of phase regarding the reference signal, which is here. And we have another signal I called the signal pulse, which permits to validate the data here. We can see this signal pulse here. So we can see that we have an NAND gate here connected to this part. So I guess that we have probably a parity, but I am not totally sure here. And 3 lines, or maybe 3 bits of the label. So we should have here a low level when the label is correct and parity is correct. So therefore there will be here a positive pulse which permits to validate the data. And there is also another signal here. This signal permits to select between the two different modes we have seen, so the absolute and the relative mode. So I think that this signal depends on the label transmitted. And there is a pulse which permits to update the output here.